I think we are ready. Thank you, everyone, for joining us. Today we have Dr. Steven Hoch as our guest speaker. He was recently appointed as Chief Technology Officer of Abrasion, and he was Head of Research since July 2018. Steve has held postdoctoral research associate positions at the University of Cambridge and at Imperial College London, where he has also completed a PhD in nanomaterial chemistry. He is a member of the International Advisory Board for the Graphene Nano CDT at the University of Manchester, and was formerly a teaching fellow in the EPSRC Center for Doctoral Training program in graphene technology and at the University of Cambridge. Steven has held the role of chairman of the technical working group within the Graphene REACH Registration Consortium. Thank you so much, Steve, for joining us today. Dear attendees, please feel to ask your questions by using the Q&A box, and we will get back to you after the talk. Steve?
Great. Thank you, Elif, and thank you everyone for the invitation to present here. So yeah, today I'm going to give a brief introduction to graphene and other advanced materials. So Viserion, we're a company who specialize in advanced materials, but also taking technology out of universities into the real world. And over the last few years, we've acquired different companies and spin-outs from universities. So we've got particularly strong relationships, as Elif mentioned, with the University of Cambridge and Manchester, where we've got two graphene spin-outs, one Cambridge Graphene, the other is called 2D Tech. So today, I mean, our real focus at the moment is looking at graphene and what it can do for textile applications. So I'm going to outline firstly what is graphene for those of you that aren't familiar. I will give a bit of overview in terms of what it can do for textiles, and that really goes into consumer and technical textiles. And then in explaining how we can actually manipulate graphene. So how can we use it? How can we make it? How can we incorporate it into textiles? And that's where our company comes in, and I'll go through some of the projects we've been working on over the last 2 to 3 years on putting graphene in different aspects into textiles. There's plenty of other materials and other properties that graphene can harness, which are more for future applications. So I'll give a bit of background on antimicrobials and wearables, which have kind of been growing over the last few years. So for those of you at the RCA that might be familiar with polymers and textiles, just wanted to explain and how similar graphene might be. So if you take something like nylon, which is called polyamide, so these are very long chain molecules. So these wiggly lines here are basically carbon atoms linked together in a long chain. And when we make a textile fiber, we are aligning these fibers, these molecule chains into fibrous structures. And so once you get that alignment of these materials, you get quite strong, quite robust materials. And so that's common to all of these fiber type materials, but with the chemistry being slightly different. So you have things like nylon, which is made up of amide groups, and polyester has different or many ester functionalities that give it different properties. So when you're making polymer fibers, you tend to use a process what's known as melt extrusion and fiber spinning. So you insert some polymer chips into a hopper, into a feeder, and that goes through a process where the polymer is melted, and then we can extrude that, and we can draw fibers and spin fibers depending on what we want to do. So graphene is very much like this, and if you consider now, rather than having a long molecular chain, you've actually got carbon atoms in a hexagonal structure, so in a complete infinite two-dimensional structure. So graphene is one atomic layer of graphite. So most of you will have worked with used pencils, and essentially graphite is the parent structure of graphene. So it's thousands and thousands of layers of graphene. And what we do is actually take graphite and we process it into thinner and thinner structures until we get down to one single atomic layer, which is very, very small. But some of the unique properties of graphene come from graphite. So most of you might know that graphite is actually electrically conductive. So if you you draw a circuit with a pencil, you can get it to light up a light bulb. And the property that causes that is electrons, so how we conduct electricity. So normally when chemicals bond to each other, for carbon, you have to have 4 bonds, but in graphene and graphite, each carbon atom is only bonded to 3 others. So that gives a unique property that there's 1 electron or one bond missing. And actually all these electrons are sitting between the layers. And that means these electrons are freely able to move around the structure. And that gives rise to electrical conductivity across the structure. You might also know that graphite is a good lubricant. So that's because we've got very strong bonds on each of the graphene layers in the plane. But between the layers, we've got very weak forces. They're just very localized forces, and that causes these layers to slide over each other. And that's how we can make use of exfoliating graphite into graphene. So really peeling away each of these layers. So graphene also, if you can make very, very large sheets, you can actually turn that into its own fibrous structures. So you can take a very infinite graphene sheet, and when it interacts with other graphene sheets, you can draw that as its own fiber. It will hold its shape, it will hold itself together. Some of you might have come across things like carbon fiber, which is very common, very high strength material, particularly now in the automotive sector. And these are really formed by taking polymer textile fibers that you see, for example, cellulose or polyacrylonitrile, and actually heating those at very high temperature to form a more graphitic and conductive structure. But today I'm going to focus more on graphene itself and what graphene can bring to traditional polymer textiles. So this slide here just shows some of the unique properties that graphene harnesses when you do make this very thin 1 atomic thickness material. So you end up with a material which can conduct heat a lot better than copper, also can conduct electricity much more than around 10 times more than traditional metals used in circuits. We've got something which is thought to be much stronger than steel. So when you get down to these single atomic units, graphene becomes incredibly strong. It's also very thin, it's very flexible, so it can tolerate a lot of damage. And in terms of the color, when you get down to that single thickness, you get something very transparent. So each layer of graphene is absorbing about 2% of light. But as you increase the number of layers and you go towards a more graphitic structure, that's why you start to see this opaque structure. So there's lots of primary benefits that we get from graphene. There's also lots of secondary benefits. In some cases, it can be antibacterial, so it can actually cause cell disruption, depending on the type of bacteria or virus sitting on the surface. It's very thermally stable, so we need to heat it to around sort of 700, 800 degrees Celsius before it starts to decompose and burn. So it can be added to materials to improve its fire retardance properties. And in graphene, because you imagine, again, it's an infinite sheet, you can put it down and it can behave as a good barrier material. So, for example, if you want to protect a surface from corrosion, you want to stop things like oxygen and moisture permeating through a structure, maybe in for example, food packaging, the graphene can really play a key role in blocking out any of these other molecules and ions. So those are kind of the main benefits that we look to harness. Sometimes we do get some benefits that we didn't expect to see in a product that are a bonus. And there are things we're still learning every day. So graphene has now been around for around, let's say 15 years or so. So first discovered in around 2004. The Nobel Prize was won for graphene by 2 scientists at Manchester in 2011, 2012. So still relatively young. And actually beyond graphene, there's a whole host of other materials that we're also looking to harness. So graphene is one of maybe 2,500 materials, which all have different properties. Some are electrically insulating, some are different colors. So that depends on what kind of light they will absorb, and it depends on their electronic properties. So some of these in between, they have orange colors, red colors, pink colors, yellow. And so you've got a whole family of unique materials that are relatively undiscovered, unknown. There are still materials that we are discovering to this day and finding new properties that exist once you go from a 3D structure like graphite to a 2D structure like graphene. And one of the other materials we're also exploring at the moment is called boron nitride. So that sits at the other end of the spectrum to graphene. So when we make graphene products, they tend to be black because we're making a bulk product with kind of a darker material. Boron nitride is a white material, so it has completely different electrical properties, but it can be used in complementary applications to graphene, used together as a kind of hybrid material. So just to highlight what graphene can bring and these other materials can bring to textiles. So because we can improve the mechanical strength of materials, in theory, we can create very thin, very lightweight fabrics that can be much more comfortable and still very effective. Or indeed, we can make fabrics and garments last a lot longer. We can improve their durability because we've made them stronger, but really not added any further material to that. There's lots of things we can do by adding multifunctionality. So there's a whole host of properties here. I mentioned things like the thermal and electrical conduction. Graphene is very chemically resistant. It has this kind of lubrication property. It absorbs UV light very well. So you can use this a lot in things like personal protective equipment, where people are going to be exposed to harsh environments. So really, this can enable not just for consumer, but also for technical textiles. It can enable innovative, more sustainable fashion. And actually, what we found out over the last couple of years working with graphene and conventional manufacturing processes is that you don't really have to change anything. It's really just incorporating a new material into existing processes. So that's very attractive because our supply chain partners don't really want to change what they're doing. So this is a kind of overview of what we've been working on. So we've taken multiple approaches to put graphene into textiles. The first and simplest has been in printing and dyeing textiles with a graphene liquid, a graphene ink. We're also taking that now into coating individual yarns. So rather than going through a printing process, you could weave fabrics with graphene that's already part of the exterior of the yarn. But we can also put graphene inside and blend graphene with polymers. So blending graphene with nylon or polyester by melt processing, and that incorporates the graphene inside the yarn. So again, you can harness some of these benefits. Putting graphene inside the yarn tends to have less of an effect on things like the thermal and electrical, because the graphene is surrounded by polymer, which doesn't have much use. So it's kind of insulating or encapsulating the graphene. So that's why we've taken the approach to look at coating on the surface with graphene that's more or less in contact with your skin, so that you can get direct contact and with something which is thermally conductive or moisture wicking to take to control that and improve the performance of that garment. So we do most of our research at two places. I'm based at the University of Cambridge within the Cambridge Graphene Centre, and recently we've moved one of our R&D teams into the Graphene Engineering Innovation Centre. That's at the University of Manchester. So that's a £60 million building that was built towards the end of 2018, 2019. And that building hosts a whole series of labs which have different specialties. So some labs are focused on energy storage, some are focused on anti-corrosion or applications or composites, and then there's a specific lab now focused on printing and sort of developing smart wearables and electronic applications for graphene on different substrates. So we do a lot of our ink production and formulation at Cambridge, and then those inks are either printed at Cambridge or sent to Manchester, where we can do the printing. We work closely with Warwick Manufacturing Group to do what we call melt processing, melt compounding. And then we take that material that's produced and we do fiber spinning. Now we do it with industrial partners, but we did some work through the University of Leeds, through an MRes in textile technology. And now we're putting some of the garments that we're making from these technologies through wearer trials. So getting athletes and people to actively wear them and monitor their performance, thermal management and moisture wicking, so we can do that in real time and provide some real life data that backs up our scientific work. And recently we've just kicked off a project with the RCA looking at a new print and design focus of some of our garments. And again, how can graphene printed in different areas or different designs, how can that really affect and influence what the wearer feels? So that's a really exciting project to be looked at. So this is graphene ink. So what you see is literally just a bottle of look like dark black or grey liquid. So inside these bottles, we tend to have something around 100 grams of graphene in a liter. That can be changed depending on what we want to get out of it. And we tend to use mainly water just because it's nice to work with. A lot of companies want to move away from harsh solvents or sort of volatile solvents. But because graphene doesn't really like being in water, we have to stabilize it somehow. And typically, a lot of research is going into things like surfactants and soap molecules, which can wrap the surface of the graphene. They can help stabilize the graphene sheets in the solution. So it's quite a famous paper about 5 or 6 years ago using a kitchen blender. So everyone at home can take some graphite, they can add some water and fairy liquid, and they can blend and make a graphene ink dispersion. So essentially on an industrial scale, we have a much larger process to do this, a continuous process that enables us to produce this more efficiently. And obviously we don't use fairy liquid, we use other kinds of chemicals and stabilizers that suit our process. So after we've made that, we get something which still looks a bit like water, doesn't really have any sort of properties suitable for direct printing. So what we end up doing is formulating those graphene dispersions, and we add different polymers and different materials to get them to do what we need them to do. So we formulate inks for things like inkjet printing all the way up to screen printing. So most of you might have used these techniques before. Screen printing, for example, is one of the most common ways of printing on textiles, but that needs something which is quite viscous. So you need something which is sort of around a honey sort of viscosity, so much more viscous than water. But what you get back from that in terms of a printing process, you tend to have quite large features. You've got quite low resolution, and your throughput is relatively high, especially if you go towards a rotary screen printing. If you take inkjet printing, for example, which you can basically use something that looks like water and print it directly, that has a much higher resolution. So you could print features down to around 5 microns. So gap sizes of electrodes or electronics that you can barely see by your eye, but the throughput there is much lower. It's a much slower, more accurate process. Then in between those two, you've got other things like offset printing, flexo, and gravure, which we use quite a lot for printing on plastics or papers. And so for screen printing, which is the route we've really taken so far, we modify the rheology by and we test this using something we called a parallel plate rheometer. So you might be able to see this video playing. So we take our ink once we've formulated it, and we sandwich it between these two plates, and that allows us to measure the viscosity as a function of the shear rate. So for example, when your graphene ink is in its bottle, there's no shear being applied. It has a very high viscosity. When you want to print, you want to make sure that the ink flows very well and it spreads on the surface. So when we apply shear in for example, when the screen printing blade goes over the mesh, your viscosity will drop, and then it becomes quite fluid. And then as you stop printing, you don't want, if you're printing a specific pattern, for example, you don't want your graphene ink to spread all over the substrate. You want it to be confined to its pattern. And so with this kind of ink, what we call thixotropic behavior, this viscosity will rebuild after we stop the printing. And so yeah, we have different polymers to do this. So we work a lot with celluloses, which can increase the viscosity at quite low concentrations. And again, depending on the final application, if we want to use graphene's properties, we want to make sure it's highly electrically conductive. The more polymer we add, the less conductive that final formulation will be. So we try to add as little amount of rheology modifier as possible, such that we can maximize the graphene performance. So these are some of the first examples. We work with we have a commercial partner, MAS, in Sri Lanka, And so we developed a formulation that works for them and incorporates some other chemicals. So they wanted us to include a polyurethane, which is what they typically use, and they can cross-link that to the fabric through adding a cross-linking chemical. So that chemical is added at their end. So we provide like a part formulation, but now we have the ability, we've developed the know-how, so we can produce everything in-house within Viserion. And so the samples we'll provide to RCA will contain all of the necessary ingredients to get these dyes, you might call them, to fix to the textile. So we started with complete dyed textiles. So these are panels which were dyed and stitched together. So here we've got graphene applied to the chest area, but also to the back. So this is really targeting active sportswear, where thermal management is very important and moisture management is incredibly important for the wearer's comfort and dryness. And so we took these and we tested them against industry standards through an independent company. And so I'll go through what kind of tests we would do. But since then, we've moved on to looking at just screen printing in certain areas. So you might just want to print the armpits and the chest area rather than the full body. And again, that's a compromise to make between things like the cost effectiveness. So how much cost we're adding. Graphene is a relatively novel material. We're not at full commercial scale at this stage, so there is a price uplift in some of these products, but it's coming down all the time. So the customer doesn't want to just put graphene everywhere and doesn't want to put it where it's wasted. Also, dyeing is quite a wasteful process, so you might expect some of the graphene might end up in the waterways, so that's not good for sustainability. So we just want to print it where we need it, and it's much less wastage of ink. So that was generation 2, and if you look under a microscope, you can kind of see the graphene is and the polymer it's with is creating like a continuous film. You can just about see the textile fibers, the weave underneath. And we took those, and I can just show if this video works. I don't know how clearly you'll see it. Let me try and make it full screen. Just a recent screen printing trial using rotary screen that we've done at the University of Manchester, printing a kind of hexagonal pattern. So let's just see if this works. So again, we designed the screen. We've kind of understand the mesh size that we need to print the graphene through, and then now we've optimized things like the substrate. We've been able to provide RCA, the printing team, with enough information to get started and looking at how we can more effectively design these fabrics. So we can understand now what fabrics work well, which kind of fabric density, what GSMs work well with our inks, what speeds we can print at, and hopefully we can now take that and look at how we can redesign and really optimize, understand what the graphene is doing compared to fabrics without the graphene. So yeah, so once we make these swatches or garments, we tend to put them through rigorous testing. So we work with BTTG and Shirley Technologies in Manchester and Leeds. And we follow this kind of framework where we look at abrasion testing. So because we mentioned graphene is a good lubricant and it can maybe improve some of the friction properties. Can we improve the abrasion? Obviously, as we're printing a pattern on a garment, we don't want it to delaminate. We want it to be fixed in place. So we also want the garment to be able to stretch and to recover back to the same shape. We want obviously the garment to be permeable. We don't want to, by covering up all of these the weave with graphene, we might expect to reduce the air permeability, and so we don't want to significantly deteriorate air permeability. We look at the water vapor permeability. We look at water vapor resistance, which is simulating the sweat evaporating. So that gives an idea of the potential comfort of the garment. And then we look at absorbency. So taking the dry fabric and dropping water on it and see how much water it uptakes, to see how long it takes for that water to absorb into the fabric. And then we look at the wicking in different directions through both vertical and horizontal wicking. And then we look at the drying rate, so how quickly can these materials dry once you've got a pre-wet fabric. I think one of the important criteria for the first set of garments, we wanted to improve the heat transfer through the fabric. So we look at the thermal transmittance, or you might have, when you bought a duvet, you get the TOG rating. So that's a measurement of TOG. And so these were some of the initial results that we saw and gave us a lot of hope for continuing this work. So in terms of water repellency, we saw an improvement of repellency when the graphene's on the exterior of the garment. Importantly, we didn't see any dimensional changes. We saw up to around 20% improvement in thermal transfer. The drying rate was much better with the graphene, and the wicking was something which is quite significantly improved. So depending on the direction, we were getting around 50 to 100% improvement in wicking. So the faster you can wick moisture away, the quicker it can dry. So you can spread it across the whole garment. In terms of the water vapor resistance, there are some industrial standards, and I think any number below 4 or 5 suggests it's a comfort, but comfort is very difficult to determine in the lab. You need to get wearers to experience what it's like to actually wear the garment, the fit of the garment. And so that's what we've been doing recently, is taking our new generation garments. So now they're sort of completely black with the pattern incorporated on the inside. And so we've hooked up around 10 athletes with kind of similar body shape and fitness, and we're monitoring all of the kind of biophysiological data, trying to collect as much as we can. It's taking months now to analyze because we've got so much data. And following the exercise, we're doing some thermal imaging. So actually the moisture that's present on the garment, it comes up as like a kind of a cold spot. As the water is evaporating, it's reducing the temperature, and we can monitor that by looking at some thermal imaging. So yeah, we've had some very promising results. We're waiting for the final report to come through, and so yeah, hopefully that can then give us some further support to our initial laboratory trials. The second aspect I want to go through, so now moving away from the graphene inks, is actually looking at what we call melt compounding. So again, it's quite a big industrial machine where you put in, as I mentioned, for fiber spinning, you have a similar process. You feed in your polymer pellets, and so we can also feed in graphene as a powder, or we can feed it in as a liquid. And then we go through an extrusion. So we have these 2 screws which are rotating inside the barrel, and what comes out is now you've got a blend between your melted polymer and the graphene inside. So it comes out, we cool it in a water bath, and then either we can collect the filament or we can chop that into pellets. So you can see there's some pellets being ending up in the bucket. Just go back to the okay, I hope you can still see that. So once we get that output, we can then we send it to several industrial partners that we use, and they are turning it into multi-filaments or monofilament yarns. We can spin them in certain directions. So this is a recent product we've made. It's a polyester spun with a SZ neutral thread. And probably about 1 year ago, we were producing monofilaments that had a diameter of around 100 microns, and now we're getting down to around 10 to 20 microns in terms of the filament range. We've also made some which are much smaller, but you don't really see any graphene on the surface. It's all now really embedded inside the fiber. So this is more for when we are looking to improve things like the mechanical performance, improve the durability of the actual textile. So I've got a few graphs here. I don't want to show too many complicated graphs, but we're still optimizing a lot of these properties. So when we make some fibers, we tend to put them through tensile testing. So we actually stretch the fibers and work out when they break and how much energy it takes for them to break. So we get three things from this. We get the tensile strength. So that's the strength, the point at which the fiber begins to start to stretch and doesn't come back anymore. We work out the stiffness, so tensile modulus. So that's how the yarn can really avoid any sort of stretching. And then we can work out the elongation. So when you do stretch and stretch and stretch, when does that yarn break? So we've got some really positive results in terms of the actual strength. So in some cases, depending on the graphene loading and the type of graphene that we're using, we've seen improvements up more than 100%, so more than double the strength, without affecting the stiffness or without affecting the elongation too much. So that's quite positive, and as I say, we're still optimizing some of these results. But what we do find is that when you put enough graphene inside the polymer, again, you can make it somewhat conductive. So just to simplify everything, when you're putting a conductive material inside an insulator, so the insulator here is your polyester or your nylon. If there's not enough conductive particles, there's nowhere for the electricity to conduct. So we don't see any change in conductivity until you start to form these kind of networks. So now in this picture, you've got a network of graphene particles, so the electricity can flow through that structure. And then once you get to a very high concentration, you can now conduct a lot more electricity, and then that starts to plateau. So with our graphene polyester fibers, we've been able to optimize the dispersion of graphene. So that's probably the most important thing, is when we're putting graphene inside other materials, it's how well you disperse it. You don't want all the graphene in one location and nowhere else. Otherwise, you'll have pockets where there's essentially, you've got some conductivity, then it's insulating again. So ideally, you want a very uniform product that's controllable. And so we're working now within a range where we can maybe achieve some of these anti-static properties. We're not quite, I don't think we'll ever get to the stage where we're making highly conductive yarns for electrical applications, but maybe for safety and anti-static applications where you might have people working in being exposed to maybe explosive chemicals or explosive environment. They might need to wear certain protective clothing to help them do that. And so yeah, we should be able to achieve these kind of properties with a graphene polymer compound. If you do add too much graphene, then some of your mechanical properties might deteriorate. So as I go back to this graph, if we add too much graphene, so this is going up to 5% of graphene inside, your elongation drops quite a lot. So you can no longer stretch the garment. Things like your stiffness also drop. So it's basically the mechanical properties and the electrical properties need to be very well balanced and finely tuned. So just the last few slides on what else can graphene offer and other materials. So over the last year or so, since COVID, we've got a lot of customers who are very interested in adding some antimicrobial features to their products, whether it's textiles or whether it's a plastic product. If you just use graphene on its own, I mentioned previously that it can be a good antibacterial material. In other cases, actually, it can promote bacterial growth. So graphene can actually be a very nice surface, and it can interact well with some bacteria. So it's not a complete solution. You wouldn't just use graphene as a kind of broad antimicrobial material. So what we do is, working with one of our companies in Spain, is we modify graphene. So this is the graphene structure, and we put these other nanoparticles, metal oxides or metal nanoparticles. So some of you might be familiar with things like copper nanoparticles or silver nanoparticles. They're used a lot in antimicrobial products, and so we do the same here. But the graphene actually can behave synergistically. It can provide a support for these nanoparticles. It can stop them from growing too large and ineffective. So it can keep the size of the particles to a minimum. And so what we found is testing them against COVID, and we've been developing these very transparent antimicrobial coatings that you could apply in hospital environments, or you could apply on any kind of product or textile. we're looking to now develop this and potentially register this and go through regulation to get this an approved product. But we're still a long way from that, but we've got very good results, particularly for COVID inhibition, looking at how we can create surfaces that protect us from COVID or can kill the virus within a few minutes. And we've got excellent results there, and we've taken that now and we're looking at other bacteria. So probably the thing that's going to kill us after COVID will be antibiotic resistant bacteria. So that's something we're working with other universities and looking at things like MRSA, Staphylococcus aureus, E. coli, and another thing called bacteriophage MS2, which is used as a COVID virus sort of replica. And we're doing tests now on a broad range of these kind of bacteria. So I mentioned with graphene, you can have a negative effect in that you can actually have a good surface for bacteria, and with E. coli, we actually get a 30 times increase in the bacterial colonies after about 24 hours, which is not good. But with these graphene metal hybrids that we're working with, and now we're trying to control the dosage, we're getting much more significant reduction of these bacteria and viruses, which is great. And that means we're now trying to look at a shorter time frame. So looking at within 1 hour, we still get similar results. We get more than 99, occasionally more than 99.9% reduction, which is kind of a minimum baseline if you want to say that your product is antibacterial or antimicrobial. The last thing I want to talk about is print electronics. So this is again something we're heavily involved in, and there are products coming to the market all the time, particularly in the sort of medical and healthcare sector. And so graphene can play a key role in all of these actually, because as a printed component connecting circuits together, we can use graphene as an antenna. We can use graphene as an energy storage. So graphene graphite is used in all of our batteries at the moment, in terms of we have ions that are going inside and outside of the graphitic layers, causing our phones to charge up or discharge. But graphene's also it's quite a good surface for sensing. So I mentioned, for example, in the bacteria case, graphene's a nice surface for some things, and we can actually change the chemistry so that we can detect certain molecules, detect certain bacteria, detect certain parts of DNA, or look at things that are coming off of food, looking at how ripe food is by detecting the chemicals that are being produced. And so we're active in, I'll just show a few of these. We're working a bit with printed circuits on leather. This is for an automotive application where the customer wants to potentially integrate, and these will be coated with other colors and other dyes. So we won't necessarily see the circuits, so they'll be invisible. They might be part of the car. They might be part of the steering wheel, for example. And we're trying to create things like switches or touchpads out of these printed buttons. So in some cases, we've still got rigid circuit boards. So printing all of these components in something that's printed and flexible is not that easy. You can see here we've got three batteries here to power the device. So again, where do we get your power from? And recently we've just finished a project working with other partners, doing a completely fully flexible printed battery, printed circuit board, lighting up a beer bottle here, for example. So there's still lots of progress to be made, and gradually things are becoming more conformable. So if you want to have a wearable on your skin, it's kind of optimizing these printing processes such that we can print on all kinds of different surfaces. This is the last one. We've been working with companies for a while now on printed flexible sensors. So these are either printed onto different plastic films or printed onto things like medical dressings. And again, we're looking at one for patient recovery, looking after knee surgery. We've been working with a company who developed the circuit board and interface to a mobile phone, so that we can look at tracking the bending of the knee and the twisting of the knee by using a printed graphene sensor. So the graphene sensor can be quite low cost. It can be disposable, or it can be can be recycled, or it can be sanitized and reused. So there's a number of things that we could potentially do. So in the healthcare sector, there's all kinds of demands now for wearable sensors for the elderly, or for pregnant women who can look at monitoring things like baby's heartbeat and the growth of during pregnancy. But yeah, also for looking at babies, looking at sensing in their cot, sensing their temperature, sensing their heart rate, sensing movement. So yeah, there's kind of an endless list of applications for these printed electronics. So I think I'm gonna finish there. I think hopefully I've covered everything that I was going to. So just to summarize, just wanted to point out that yeah, graphene is hugely exciting. I wouldn't say we're still early stage, but we're now ready for commercialization. It's seen kind of a rapid explosion of interest in academia and industry over the last 10 years. And yes, in some cases now, for example, our coated printed textiles, we are ready to commercialize those and really scale up. We've shown that we can produce and manipulate graphene using conventional printing processes and extrusion. And we're now looking at validating all of our data using independent test houses, but now we're also doing further wearer trials which validate further these test results. And because we've got so many properties to play with, we've got a whole library of new materials that, again, we haven't yet discovered, or very little work has been done in the lab. We're hoping to see continual development of garments and products for the textile sector. So that's it. I just want to thank the teams that we have working on these applications. There's 3 scientists that are going to be heavily linked working with the RCA on this current project. So a couple of them are here on the call today. So we've got Dr. Mayank Gautam, who's based in our team in Manchester. And we've got Thanuja and Daniele, who are based as scientists within our team in Cambridge, as I mentioned, making all of these inks, doing some trial printing. And hopefully, we'll be learning from RCA more about actual textile fundamentals, and hopefully this will be a great partnership. Thank you, Elif.
Thank you so much, Steve, for this super interesting talk. There's so many opportunities. That's why I encourage everyone to put questions into the Q&A box, because it's a privilege to have you, Steve, and the Versarium team today, and you might not find them again, at least in this year. So I think we have one question. Mary asks, are there any circumstances where the wearability has adverse effects to the wearer, or some people allergic to it, for example? Do you have any allergy or toxicology results, or have you explored this field?
Yeah, so we've done some, actually we did a test with BTTG, actually using, I think it's a test they developed with Marks and Spencer to look at things like skin irritation, and there's a whole list of known chemicals that cause allergic reaction. And so what they do, they take your textile, they soak it in different types of solution, and they measure things like the pH and what chemicals might be coming off. And so we haven't seen any negative test results. In terms of graphene itself, we are part of what we call the REACH consortium. So because we've scaled up graphene beyond sort of 1 ton per year, we have to report the toxicological tests, and we've been doing a lot of work with some of our other competitors as well. We're working as a consortium, and so far there's been no negative kind of test results. Graphene has not shown any sort of irritation. There's a lot of animal testing that they have to go through for European regulation. And then later on down the line, if we want to scale up, for example, beyond 100 tons or beyond 1,000 tons, there's lots of long-term studies that have to be done in terms of sort of, is it carcinogenic? Is it going to, how does it break down? Does it interact with, does it affect composting and things like that? So we've got some really good recent results showing We've put graphene through a composting process, and it has no effect on the kind of ecotoxicology. But yeah, there's still lots of tests that have to be done, and yeah, this is quite a novel material, and the rules are changing all the time. So yeah, graphene is now it's explicitly defined as a nanomaterial, and so we have to do all these tests. And as I say, so far there's been no negative results.
Thank you. We have one technical question from Sid. He thanks you for this interesting talk. He said that he is interested in what the difference is in the moisture and thermal regulation of the graphene garment, if the print covers the entire surface or in just a pattern like you show it with the rolling printing.
Yeah.
The rotary, yeah.
This is exactly what we want to work with you guys for, to understand and to try printing different designs and see. We think that we need to have this kind of network. We're printing it as a continuous network so that moisture can be wicked through that structure rather than having it as discrete patches of graphene. So we know that we need to have this network, and also having the print on both the back side and the front side of the garment, because can that allow us to help us wick the moisture through or take the temperature through the garment much more effectively. So there's still lots that we need to understand, and yeah, so I can't really answer that at the moment. We've done tests, and yeah, we're still to kind of really fully understand what the effects are of design, and also different textiles will play a key role. So polyamide will behave differently to cotton, and yeah, we're going to have to look at the effect of graphene on each of these different types of textile.
Yeah, following up on those notes, I know you work with different textile partners. RCA is one of them. We recently started a project together. So what are your textile challenges? How do you feel about working natural fibers or some new fibers, some natural new resources?
Yes, so far we've mainly worked with like synthetic polyesters, and these are blends with things like elastane, spandex. So yeah, we need to broaden our understanding and understand what effects different kind of densities of fabrics have and how the print is changing on these fabrics. So we've done some preliminary studies. We know that we can print on cotton, polyamide, and different blends. But yeah, a lot of customers are wanting obviously to use more recycled fabrics, and yeah, again, we need to do this work and understand where we can source these types of material from, which customers are using different fabrics, because we expect that we will be taking a fabric from our customer, something they typically use, and we'll be applying our print on top of that, or we would be supplying a graphene polymer blend that they can then or we can then weave that or spin that into their configuration. So yeah, we have plenty to learn, and there's it's a massive area, and I think a few of the guys went out to Premier Vision last couple of weeks, and yeah, it's a minefield of so many different fabrics and types that we need to investigate.
So actually, I have another question about sustainability. So we have a critical mass in the program actually in terms of student numbers, prioritizing the sustainability. What do the graphene promise in this context?
Yeah, so two things I mentioned briefly earlier, that if we can improve the strength of fabrics, maybe they'll be more durable, they can last longer. But I guess most of this, if it's a fashion item, people they throw it away not because it's worn out, but because it's gone out of fashion. So yeah, there's also opportunities for example, recycled plastics. They're not always a high enough quality to be used in garments. So it could be the case that to get them to be able to use more recycled content of our fibers, we can add a small amount of graphene so that we can get them to a high quality. And also in terms of recycling materials, if there's graphene inside the polymer, as we keep processing them, they become weaker and weaker. So if we can offset that by being able to use a polymer more cycles than we could normally, then again that will help in terms of aiding sustainability. I don't know, David, if you had any other comments to make on that.
Not really, Steve. I think you've covered it. Sustainability part of it is obviously, really critical. But I think the important thing is, certainly from, a lot of the things I'm reading lately, that extending the lifetime of garments is going to be quite a big thing. And certainly graphene is going to play a big role in being able to do that. So, but no, I think you've covered it perfectly there.
I think Emma has one question. Emma, would you like to ask it yourself, or?
Yeah, sure. Thank you for the presentation, Steve. It was really, really insightful. Mine's just kind of quite like a general question. How does graphene, its antiviral properties perform? How does it physically be antiviral?
That's a good question, actually. It's still not very well known, but yeah, things like the metals will act in a chemical route that's well known in terms of silver nanoparticles. They release some silver ions that can disrupt the virus or cells. In terms of graphene, it's more of like a kind of a softer approach. Sometimes it can be a physical nature where it just absorbs the molecules and doesn't let them go. In other cases, there might be some transfer of electrons or something else that can disrupt the cell walls of the virus and bacteria. So yeah, it's still very much early days and understanding, and that's something we need to do if we want to add graphene or sell it as an antimicrobial material. We need to prove the mechanism. Is it a physical nature or is it chemical? And we're not there yet.
Thank you. Thanks.
So we have two more questions, and then I'm just gonna finish the lecture. But how sustainable is the process of sourcing the graphite and converting into graphene? Poppy asked this question.
Yeah, so good question. I mean, graphite is a natural material. It can be naturally mined, and it depends on our process. So we actually, for our graphene inks, we're using a synthetic graphite, which is made at high temperature in a furnace. But there's sources of graphite all over the world. It's not an endangered resource. Actually the good question is, yeah, we're trying to at the moment understand our carbon footprint for all of our processes, and so we've got a process which is very efficient, and we're using just water, and we're not actually wasting anything. We're using everything that comes out of our process and formulating it into those inks. But there are other companies who are producing stuff with sort of nasty solvents and using quite aggressive chemistry to produce their graphene. So we're at an early stage. We've recently hired a head of sustainability because we see that as a big driver for many applications, not just textiles, but things like construction sector, where we put our graphene into to replace cement, which is one of the world's biggest polluters. And so we should be able to offset a lot of the carbon that's being produced by this industry. I think that sort of answered it. I might have answered a different question, but hopefully it's enough.
Okay, thank you so much. There's just, I think, one question about the workshops and studios. I can answer that. So as Steve said, if you are using a water-based graphene ink, then you can use the facilities in Kensington campus, Textile Studios. But if you are planning to use any solvent-based one, then you need to request a booking in Battersea printing room, because then you have to, I mean, in any case, you have to be very careful about health and safety, and you should share this material safety data sheets with the technicians.
Sure. Yeah, all this will be supplied, but we like to stick with water, as you said. It's much easier to work with, and we can provide all this. Thank you.
Thank you so much for joining us today, and thank you, everyone. So I'm just gonna end today's session.
Great.
Hope you had enjoy as much as we can.
Thank you, Elif. Thank you, Steve.
Thanks.
Thank you, David.
Thank you, Elif. Thanks.